Bienvenidos a la ASERSA Open Webinar Series 12, un espacio organizado por ASERSA y aguasresiduales.info, desde donde queremos poner en valor la regeneración y la reutilización del agua. Soy José Miguel del Arco, buenas tardes a los que nos seguís desde España y Portugal y buenos días a los que lo hacéis desde América Latina y gracias a todos por vuestra asistencia. Antes de dar paso a Rafael Mujeriego, presidente de ASERSA, para que nos presente a los invitados de hoy, permitidme que os comente que la webinar de hoy está compuesta de un primer bloque donde hablaremos sobre el caso de reutilización de Windhoek en Namibia y el caso de abastecimiento alternativo de agua en la ciudad de San Francisco, en Estados Unidos de América, en un segundo bloque. Ambos espacios tendrán una duración de unos 45 minutos aproximadamente cada uno y a la finalización de cada bloque abriremos un espacio de dudas y consultas que nos podréis ir dejando en la pestaña de preguntas. Aunque la presentación es en inglés, recordad que nos podéis dejar vuestras consultas en castellano. Mi compañera Tina estará coordinando el chat durante toda la tarde para cualquier cosa que necesitéis y el material de hoy lo tenéis en la pestaña de app, en concreto en compartir medios, y ahí podéis descargarlo. Y sin más, doy paso a Rafael para que nos presente a los invitados de hoy. Rafael, buenas tardes.
Buenas tardes, José Miguel. Muchísimas gracias. Es un placer estar aquí hoy una vez más contigo, con todos nuestros oyentes y sobre todo con dos invitados especiales. Es un placer poder celebrar una vez más el webinar número 12 bajo la tutela de aguasresiduales.info y ya sin más tiempo voy a pasar a hacer una breve presentación, introducción. Yo lo haré en castellano y nuestros colegas lo pueden leer aquí en inglés. Pues bien, en primer lugar, sean buenos días. Yo sé que nuestra invitada Manisha Kozari está recién levantada. Buenas tardes y buenas noches para todos. Bienvenidos al webinario número 12 de ASERSA. Muchas gracias a todos por asistir a este nuevo webinario, el segundo de la Open Webinar Series 2022 de ASERSA. Como muchos de ustedes ya conocen, nuestro objetivo es compartir y divulgar los más diversos proyectos que se están llevando a cabo para hacer de la regeneración y la reutilización del agua un elemento básico de la gestión integrada de los recursos hídricos. Siguiente pantalla, creo que ha pasado. Sí. Este webinario ha sido posible, está siendo posible, gracias al apoyo continuado de nuestros 5 socios protectores: la Agencia Catalana del Agua, el Consorci d'Aigües Costa Brava Girona, la Entidad de Saneamiento y Depuración de la Región de Murcia, ESAMUR, la empresa Aguas de Barcelona, ACBAR, y la empresa Veolia España, junto con todos nuestros socios de número. Igualmente importante ha sido el interés y el apoyo ofrecido por tantos de nuestros amigos, colegas y profesionales del sector de la reutilización. Todos ellos han estado y están dispuestos a compartir con nosotros sus conocimientos y sus experiencias sobre cómo implantar y cómo llevar a cabo la reutilización del agua, bajo las más diversas condiciones ambientales, sociales y económicas. Este webinario, el webinario de hoy cuenta con las aportaciones de 2 invitados de excepción, especializados en la reutilización del agua en ambientes urbanos y muy específicamente para el suministro de agua de consumo humano. El primero de ellos en la ciudad de Windhoek, se pronuncia de una forma inusual, Windhoek, la capital de Namibia, donde esta práctica de la reutilización directa potable viene funcionando desde 1968. La segunda presentación se lleva a cabo en la ciudad de San Francisco, que todos ustedes conocen, en California, donde las condiciones demográficas, hidrológicas, medioambientales y climáticas más recientes están llevando a la necesidad de explorar nuevas fuentes alternativas para el suministro de agua. Nuestra más cordial acogida a nuestro invitado y a nuestra invitada de hoy. Tenemos un gran interés por conocer todos los esfuerzos y todos los éxitos que están teniendo sus iniciativas. Y dicho todo esto, ya paso a hacer la presentación de nuestro primer conferenciante, el señor Ivan Pusad, colega y amigo de muchos años, que ya nos ha acompañado en anteriores webinarios. Iván Pusat es un gran experto técnico en tratamiento de agua, con más de 20 años de experiencia en la purificación de agua, adquirida en sus diversas posiciones dentro de la compañía Veolia, tanto en Francia como en los Estados Unidos y en Australia. Su actividad ha estado enfocada a la investigación, la innovación y el soporte técnico en los procesos de filtración con membranas. Y dicho esto, ya doy el paso. Por favor, José Miguel, puedes poner la presentación y doy la palabra a Iván Pusat. Tu peux y aller quand tu veux. Yo recuerdo la importancia, tenemos 40 minutos de presentación. 40 minutes of presentation plus 10-15 minutes of debate.
Gracias, Rafael. Buenas tardes a todos. Thank you very much. It's a pleasure to be here always. I'm sorry I have to speak English because my Spanish is way too bad. So maybe in a few years' time I will be able to speak Spanish fluently, but for the moment it's got to be English. So can you put my presentation? Yeah, it's coming. Right. Thank you. So today I'm going to talk about Windhoek. Windhoek, as mentioned by Rafael, is the capital city of Namibia, located in the southern part of Africa. And for us in the water reuse community, it's a very interesting case study, and it's been for a decade, for 5 decades already. Because in 2018, Windhoek celebrated its 50th anniversary of direct potable reuse. So they were a pioneer a long time ago on something that might eventually become a solution for many places around the world. All right, so let me get started with that. So you see 2 pictures there. The first direct potable reuse plant that was built in 1968, or commissioned in 1968, which had a capacity of 4.8 megaliters per day. And the new DPR plant, direct potable reuse plant, on the right-hand side, which was commissioned in 2002, with a capacity of 21 megaliters per day. These 2 assets, the first one was decommissioned, the other one is still running to date and still producing potable water for the community and inhabitants of Windhoek, have been milestones in the development of water reuse for potable purposes, globally speaking. So this is what I'm going to talk about today. I'm going to travel back to the past and give a bit of background as to why direct potable reuse was even considered in the first place, then implemented, how it was eventually implemented back in the 60s, what was the impact of public acceptance on this practice, which was completely new at the time, the impact that this has had on the community and the city of Windhoek, generally speaking. And then I'm going to transition to the future. So what is going to happen in the next few years for DPR and the city of Windhoek specifically. Okay, so for those who don't know Namibia, it's a country that is basically a country of 2 deserts, the desert of Namib and the desert of Kalahari in the south of Africa. The Namib desert is extremely dry. It's a very beautiful place, but not a very welcoming one for humankind. Very difficult to live in this place. The Kalahari is a bit more welcoming, but still very difficult conditions, very dry, high evaporation rate. And if you look at Namibia particularly, so that's the country that is located on the west coast, just north of South Africa, you see that there's absolutely no perennial rivers across the country, which means that they do have rivers with water flowing part of the years, some years, but definitely not all year, all the years. So they have a lack of surface water resources. So definitely not a welcoming place for humankind to live in and be installed. Yet the population started settling. So I think there's a problem with that slide. But anyway, population started settling in Namibia from the 19th century and started to grow in the early 20th century. They had water resources based on wells primarily until the first dam, the Avis Dam, was built, you see, in the first part of the 20th century. But what happened, and I'm going to show that on a slide afterwards, from after the Second World War, they had a massive population increase in the city of Windhoek, with the population doubling pretty much every 5 years for a period of time. And as you've seen, it's a place where water resources are very constrained. So there was a big unbalance between the water availability and the demand, the growing demand. So they looked at different options. You see that before the 60s, they had 3 sources of water, 2 dams, the Avis Dam, the Goreang Gap Dam, and the aquifer as well, that they were getting water from. But these 3 resources combined could not meet the demand on a sustainable way. So they had to find alternative ways of securing their water supply. This is the chart I mentioned just before. Looking at the population increase, you see that just after World War II, they have a massive immigration from Europe, primarily, that drove the population in Windhoek to double every 5 years, pretty much. So from 10,000 to 20,000 and then 40,000 in just in less than 20 years. And then they also had movement of population from within Africa to the capital city. So a huge spike in population at that time, and a mismatch between the water available and the demand. So they had to stop and think as to how they were going to supply this population with water in this very adverse environment. The first thing they did quite effectively, I would say the low-hanging fruit, was to cut on water losses, which they did quite effectively. They reduced the water losses in a short period of time from 20% to 7.5%, which is definitely a good mark. And by this way, they were able to save on water. They looked at other sources of water, so additional dams, transfer from interconnection from dams. Some options were deemed not economically viable, so they were discarded relatively quickly. 2 dams were deemed feasible but expensive, particularly the Gamams 3 dam. So they were not put as a priority. And eventually what came out as a priority and the most feasible option was DPR, so direct potable reuse. So that was treating secondary effluent to a higher standard to be used as potable water directly. Back then, it was a massive difference in mindset. I mean, we were still considering drinking water from one side and wastewater on the other side, and nobody was thinking about closing the loop. So that was a very, very massive change in consideration of water supply management. But eventually, they thought that they could, provide up to 33% of their drinking water from DPR, from recycled water. It was deemed feasible, but it was difficult to convince the city people. And eventually it took a bit of time to be implemented. I want to stop a little bit and come back, because maybe not everybody is familiar with this concept of direct potable reuse. Usually we talk about direct or indirect potable reuse. The difference is that for indirect potable reuse, you take a secondary treated effluent, you treat it further, you polish it, and then you send it back to an environmental buffer before it is then further treated for potable water production. So this environmental buffer can be groundwater, can be an aquifer, or can be a surface water, can be a dam. And in this dam, you have dilution factors, you have long hydraulic retention time. So you have a few things happening that are effectively considered as a barrier, an additional barrier in terms of risk management. Now, if you go to direct potable reuse, you don't have this environmental buffer. So you have your drinking water plant, your distribution system, your water users, so it can be municipality, it can be industrials. You have your wastewater treatment plant, and then you have your advanced tertiary treatment plant. And from there, you send it either at the inlet or at the outlet of the drinking water plant directly without passing through an additional buffer. And in Windhoek specifically, this is what happens. So you have the conventional wastewater treatment plant that is sending secondary treated effluent to a small pond where the water is pumped to the advanced water treatment plant. I'm going to present the process that is currently used on this plant. And then the finished water from this advanced water treatment plant is potable water and is sent directly to the distribution system where it's blended 1/3, 2/3 with water from other sources to be distributed to users. So this is direct potable reuse without passing through an environmental buffer in between. Okay, so now I'm going back again in time to the 60s. What happened for potable reuse? So it was planned initially in the early 60s. It was delayed. It took a bit of time to convince people. They had to go through extensive piloting from 1962 to 1965. And eventually they signed off on the design and construction of a 4.8 MLD plant to be implemented. And first water was produced on October 1968. So that's 54 years ago, almost. And was distributed. And immediately that accounted for 15 up to 25% of the total supply of potable water to the city of Windhoek. So the impact was immediate in terms of water resources for the city. Then other dams were built and the capacity was increased in the following years, in the 70s. And eventually, this is a slide at the same time in the US showing that they were started also to gain increase on direct potable reuse at the same time as this scheme was put up and running in Namibia. So the impact in Namibia, in Windhoek, was immediate and very significant, of course, but the impact on the scientific community, this is a paper from the American Water Works Association journal, was also quite significant. So in the 70s, they started building other assets and improving the other assets. So after a few years, in the early 80s, the first DPR plant was considered as a research facility and not so much as a production plant anymore. So it was downgraded in terms of importance and significance for the supply in the Windhoek area. Now, okay, these are a few pictures from the old plant that was built in the 60s and that was eventually used after the 80s as a research facility. But they had another massive drought in the 90s in Namibia. And therefore, they had to reconsider the use of DPR as a way of enhancing the water resources and securing the water supply. And eventually, in 2000, they ordered a new plant with an increased capacity, a more modern plant for a combined capacity of 21 megaliters per day, following the same path. So taking secondary treated effluent, polishing it, and then sending the water directly into the distribution system with a blending ratio of 1/3 of recycled water maximum to 2/3 of potable water from other sources. Okay, this is a bit of a recap of all the things that happened. I mean, the initial wastewater treatment plant were just biological filters. It was upgraded in the 80s to activated sludge for nutrient removal. So the biological process was improved in the 80s, and then in the late 90s and early 2000, the new plant came online with an additional capacity. You see also that the plant capacity was increased over the years. following the trend of the demand that was increased. Okay, so the principles of direct potable reuse in Windhoek, and I stole this slide from the city of Windhoek themselves. So they have different layers in terms of managing this scheme for direct potable reuse. The first one is a segregation at the source. So they need to control the source to ensure that there's minimum industrial discharge into the sewer, that they can control the quality, that the biological treatment is going to be optimal and effective. So there's a quite tight control of source water, and particularly on industrial discharge. Recently, in 2010-15, I can't remember the exact date, they built an industrial wastewater treatment plant, so that is absolutely dedicated to industrial effluent, to be able to collect all this effluent and treat it to a satisfactory level, while segregating from the sewer network that is feeding the DPR plant. Also, of course, they have a whole cycle monitoring from source to tap. They monitor the effectiveness of their biological treatment. They have improved the performance of the treatment in the 90s, as I mentioned. They have the DPR plant, which is based on a multiple barrier process, which I'm going to describe in a bit more detail after that. They've got the blending of final effluent that I mentioned, with a maximum ratio of 1/3, 2/3, 1/3 DPR, 2/3 potable water from other resources. And then what is very important, of course, is education and communication. Engage with all stakeholders to ensure that they are comfortable, that they understand what's happening, that in the source water, that people are not putting any risk into the sewer by any means. So all these blocks effectively form the different layers of management of DPR by the city of Windhoek. Okay, so the multiple barrier treatment. I'm sorry, it's a bit small, but I'm going to go through different process steps. What you see here is a schematic diagram of the different process steps treating the water from secondary treated effluent, so effluent that would otherwise go back to the environment, to potable water standard. So it's a complex process chain. You've got multiple barriers to look at all the type of risk that have been identified in the water. So from pathogens to macropollutants to micropollutants to radionuclides and so on. So the first step, oops, I think I've got the detail. Okay, and also something very important I wanted to mention. Initially, the plant was designed to take water both from the wastewater treatment plant, the Gamam's wastewater treatment plant, and from the Goreanghab Dam, which is a small surface water dam next to the plant. Eventually, they decided to stop taking water from the dam for a few reasons, but the main reason is because a lot of informal settlements developed near the dam, and they couldn't control the quality of the water coming from that dam. They could control the quality of the water coming from the wastewater treatment plant, but not from the dam. So they decided, and this was probably before 2015, because the first time I went there in 2015, they had stopped already taking water from the dam, that they would not take water from the dam anymore, that this natural but polluted surface water resource was not suitable anymore to be part of that process. So today they are just taking secondary treated effluent to feed the plant. So we can consider 3 blocks basically in this process. The first one, which I've called pre-treatment, very basically speaking, is mainly dealing with suspended solids and particulate pollution. So you've got a pre-ozonation, which is effectively the off-gas from the ozonation stage being added at the inlet. You've got a coagulation and dissolved air flotation step, so to provide enhanced removal of solids. And then you've got rapid gravity sun filtration. So you've got a few barriers here to provide a quite effective tertiary treatment, but there it's not yet a potable standard. But this is already good recycled water quality at this stage. The next process block, if you want, is the advanced treatment, and it's effectively combining ozonation with biological activated carbon filters and granular activated carbon filters. So through this step, effectively, you're doing two things. The first one is quite an intensive disinfection process through ozonation. And the second one is the removal of dissolved organic matters and dissolved micropollutants. You break it down first through the ozonation process, because most of the organic matter that comes back from the wastewater treatment plant is hard, non-degradable matter. Then it's processed through a first layer, a first step of activated carbon filters that operate in a biological mode. So you have a combination of adsorption, degradation of this organic matter and organic molecules. And then you have a second layer, which is effectively a polishing of activated carbon filters that works just with adsorption and no biodegradation. So this process is very effective because that's how we control a lot of hazards in the source water, effectively the pathogens first, and also all the micropollutants. And then the last block of treatment is the final polishing and disinfection, and it combines ultrafiltration membranes, so very fine filtration. These membranes are commonly used for potable water production, chlorine disinfection, stabilization, and then distribution and blending in the potable water network. So quite throughout process step, you've got 10 steps in total. Combined, that's a very effective multi-barrier approach. Okay, I had to put a picture of the team there because these are my dear colleagues from there. They've got they deserve a lot of credit. Okay, so I'm not going to present the results in terms of water quality from the plant. I mean, since 2002, there's been a lot of research done on this plant. I think the latest piece of work was conducted by my colleague and friend, Joseph Leinsteiner, who worked on antibiotic-resistant bacteria and genes. This paper was published earlier this year. So there's been a lot of work done on this plant, pretty much showcasing all the performance and the quality of the water produced from the process. So I'm not going to spend much time on that. I'm sure you can find different sources if you need to get access to this information. So I'm switching now to public acceptance, which is, of course, a big aspect that everyone has to consider when considering potable reuse, and particularly when considering direct potable reuse. So there was a press conference organized by the city in 1968. So you see that November 1968 is actually post-commissioning of the plant. So the communication process before the plant was put online was actually quite minimal. They waited until the plant was up and running and that they had the first return and lack of problems to start engaging with the population. That's what the chief scientist report said at the time, that they did not reveal too much. So they didn't went too loud. They didn't go too loud about the fact that the potable water, part of the potable water was coming from the wastewater treatment plant. But effectively, the impact and the relief in terms of access to water was very well perceived. So the positive impact was well perceived. The history of the water was not effectively communicated back at that time. through successive years, there's a few signs that show that public acceptance was quite positive. They went through additional water crises in the early 80s, and the city council was actually criticized at that time because they had downgraded the first DPR plant to research facility, and that's effectively wastewater or secondary effluent was going back to the environment instead of being reused effectively for the population in Windhoek. So they had an opposition from the public that this water was wasted and not reused. And again, in the late 90s, the public complained about the pressure they had on water resources and the fact that water was available from the wastewater treatment plant and not being used effectively. So that was a driver to expand or build the new DPR plant in 2002. Now, there's been a study more recently. I don't have the exact year, but I think it was just pre-COVID in 2017 or 18, looking at how drinking water was perceived and how much they knew in the city of Windhoek. So the vast majority of the people said that the water was good enough to drink and that was safe to drink. So quite positive in terms of perception on that front. The fact is that even in Windhoek, not a lot of people understand where the water is coming from in the first place, and what is the history of the water and what has happened from wastewater treatment to DPR. Because you see that less than 50% of the population was actually aware of direct potable reuse being implemented in their city. This may sound strange, but if we look at France, for instance, Veolia conducted a study very recently, and we see that very few people actually know what happens with water, how wastewater is treated, how it's restituted to the environment, where drinking water is coming from. There's a lack of knowledge, generally speaking, from the public. And so these results are not that surprising. In terms of impact, what we can see here is the percentage of potable water coming from different sources, so from surface water, aquifer, reuse for potable purposes and reuse for non-potable purposes, depending on whether you're not in drought situation. So that's the chart on the left. So not in drought, a lot of water is coming from surface water resources. And in drought situation, this is reduced. And effectively, the percentage of water coming from other sources is increased. You see that they tap into the aquifer during a drought period. They also reduce significantly the consumption. You see that water demand management has an important impact because they can reduce by 15, 20, 25% the amount of water that is required during a drought. So these mitigations are important, and therefore it increases the percentage of water reuse into the balance, into the mix of water supply for the city. But it's limited to 33% for potable water purposes. I think I've got a few more slides. Okay, I'm going to skip that one because it's the same thing. Okay, so what is going to happen in the future? What you see on the graph here is the evolution of water demand for the city of Windhoek over the past decades, and you see that the trend is going up all the time. So there's a few bumps, and every time it goes down, it's because the city was in a water crisis situation, and they implemented a water demand management response. But effectively, whether it is in terms of quantity or quality, the city of Windhoek is facing still a huge challenge, and they need to consider additional water resources. They have looked at different options from water transfer from perennial rivers, so that means 700 kilometers of transfer from the nearest river, They looked at seawater desalination, but Windhoek is almost 350 kilometers away from the sea, and it's 1,300 meters above sea level. So the cost would be just tremendous, not just for treating the water, but transporting it to the city. And the last option that was considered was also to build a second direct potable reuse plant. So among these options, the most feasible option, at least the one that is looked at the most seriously at the moment, is the increase of capacity for direct potable reuse. They are considering building a second plant of equivalent capacity, so 20 to 25 megaliters per day for DPR, for direct potable reuse. They will have to change the process though. They will have to put a barrier for dissolved minerals because through recycling they are increasing the salinity in the city of Windhoek, which is something that is to be expected. So they need to have an additional barrier for dissolved salts on this process, which creates the huge challenge of what to do with this brine. Because if you put a reverse osmosis membrane, which is the common process, then you have a clean water stream, and then you've got to concentrate a brine stream. And being so far away from the ocean, not having any brine aquifer or saline aquifer creates a lot of issues. So it means they would have to push the recovery of the RO as much as possible and deal with this reject as a waste, which implies cost, of course. But it also creates an opportunity, because if they, during periods where they don't need this for direct potable reuse purposes, they may be able to recharge aquifers as well. So switching from direct to indirect potable reuse, depending on the need. This is a work in progress. There's nothing done yet, but it's certainly looked at quite significantly. Okay, so I'm going just to conclude with that presentation with a few messages. I know that some of you might not be completely sure about that, but I can tell you that potable water can be produced from secondary effluent. I've been drinking potable water or water from 3 different wastewater treatment plants in Australia, in Namibia, and in Singapore, and I'm still alive. So, and I wasn't even sick. So it's completely doable. It's safe if you put the right conditions. It's a practical and economical option, depending on the options you've got on the table, but you know, it can be economical compared to other options. Certainly in water scarce area, it needs to be looked at in combination with other options, of course. You know, the low-hanging fruits that we mentioned, cutting on water losses, optimizing water demand are the low-hanging fruits. But once you've done that and you're still unbalanced for your water supply versus demand, then you need to find alternative resources, and this is one that needs to be looked at, certainly. It's not easy to implement, and the main barrier is public acceptance. So that's the key challenge. I am an engineer. I'm sure that we've got a lot of engineers on this call today. It's something that requires different skills. So we need to work with people who understand messages, communication, engagement. It takes time, but that's something that is absolutely critical and that needs to be considered. Since it requires effort on that front, it requires commitment. It requires commitment, and it requires a political will, because if you don't have a political driver, strong political driver, it will create situations where you can jeopardize your project effectively with uncertainty, with creating doubt. It's a risk for any project, but especially when you are considering something as sensitive as potable water reuse. And finally, it requires professional operation, continuous monitoring, training, research to improve and adapt to the new challenges. So once you've delivered your scheme, it's not the end. You need to continue working on it all the time to ensure that it remains state of the art, considering all the new challenges, emerging pollutants that are coming online every day. So I think the case study of Windhoek is a tremendous success, and one that we should draw inspiration from, because if we consider that 50 years ago they managed to do it, this was way before any guideline for potable water reuse was produced, way before a lot of things were done, and that it's still running today. It's certainly an inspiration that we can change our mindset and we can change a lot of things to switch from what might become unsustainable water management practices to something more sustainable. I just wanted to thank some of my colleagues from the city of Windhoek and from Wingok, the operating company of the plant, so Thomas and Pierre more particularly. And in the presentation, you will see quite a few links where you can draw more information on Windhoek if you're interested, and you can always contact me if you have questions that I don't have time to answer today. Thank you very much.
Bueno, muchísimas gracias, Iván, por esta magnífica presentación. Verdaderamente, como tú has resumido al final, una fuente de inspiración. Yo tengo numerosas aportaciones o reflexiones que hacer porque tuve la gran fortuna de visitar estas instalaciones en el año 2013, junto con otros colegas, porque se celebró en Windhoek el Simposio Internacional de la IGUA sobre reutilización de agua. Y tuvimos ocasión de vivir en Windhoek. No había sequía en ese momento, pero sí pudimos ver las distancias, eso que aquí se llama una larga distancia, allí pueden ser 400 o 700 kilómetros, y la necesidad. De manera que muchísimas gracias. Ahora yo prefiero dar la voz a nuestros participantes, a nuestros asistentes a través del chat, y al final de nuestro periodo, antes de que sean las 5, yo me reservaré, o José Miguel le pediré que me reserve un turno breve de palabras para hacer algunas reflexiones finales. Por lo tanto, adelante, José Miguel.
Sí, Rafael, nos pregunta Pilar Suárez que su consulta es que ¿cuánto tiempo lleva que las personas aceptaran el uso de las aguas en la ciudad o en el país?
Okay.
Vamos a ver, Iván, discúlpame. Si tú entiendes el castellano o el español de José Miguel, perfecto. Si necesitas ayuda, levantas la mano y yo te hago una breve traducción.
No estoy seguro, pero I think that it means how much time for people to accept
Yes.
potable water reuse. Okay, so in the case of the city of Windhoek, it was a bit particular, and I would not recommend to take that path today because they responded as an emergency, and eventually they built the plant, started it, and then communicated about it afterwards. I think today what we see is that we need to take time. So taking time means you need to start communicating about water preservation, water resources, water scarcity, engage with people. And then you need to start talking about why you need alternative water resources, what are your options, how much it costs. Once you've done that, and you have identified potable reuse as the best option, potentially,
Ya la tengo, Tina, yo pasada.
the one thing that works is demonstration. And demonstration means a site where you put a small pilot plant, where you produce water, where people can learn about it, they can see it, they can touch it, feel it, eventually drink it. And for that, if you put all that together, from the moment you need, okay, I need to find, or from the moment you say, I want to move to potable water reuse because this is my best option, to the moment it happens, it's easily 5 years. For the engagement process, the demonstration, the construction and starting, so it's easily 5 years.
Ok.
Muy bien.
Okay.
Adelante, José Miguel.
Gracias, Iván. Mira, Iván, nos dice Rubén Brandán que la mayoría de los trabajos de investigación que ha leído solo mencionan aspectos relacionados con la calidad del agua que logran el estándar de calidad. Pero nos pregunta que si habéis estado haciendo algún estudio de salud sobre los clientes o la población local que toma o que bebe ese agua.
Okay, this one I did not understand. So can you ask it in English?
The question is, there are plenty of scientific publications on water quality. Is there something similar on the public health impact of drinking that water among the population?
Yeah, so there have been surveys conducted on the water quality, of course, and the impact of potential outbreaks on the population through this water. And there's been no conclusion that drinking this water was more problematic than drinking any other tap water. So, in France, we don't have reclaimed water or direct potable or indirect potable reuse, but we have drinking water plants that are taking water from a surface river. Upstream that intake, you've got a wastewater treatment plant. So we do have outbreaks happening. And the risk from this plant in Namibia, what has been estimated is that it's not worse than the normal risk that you have from drinking water from surface water resources. So the impact again has not been found negative on that front.
Gracias, Iván. También nos pregunta Rubén que cómo se gestionan los microcontaminantes absorbidos por el carbón activo granular.
The micropollutants.
Micropollutants through activated carbon.
Okay, so there's been quite a bit of research done looking at target molecules, but also looking at bioassays for looking at the water quality and the micropollutants. The thing is that when you get out of this plant, the total organic carbon is less than 1. So you have a very high level of treatment of the water. And effectively, we couldn't find a lot of micropollutants left. I mean, certainly there are some that are going through the ozonation and the carbon biodegradation adsorption process, but not to levels where it should be a concern for the human health.
Ok, Iván. Zaher te felicita por tu presentación y nos pregunta que ¿cuántos años sobreviven los medios GAP y BAC antes de ser reemplazados?
So the biological filters are not replaced; they are topped up because there's a bit of loss through attrition, and but they are not replaced. So effectively, it may be a 10% per year replacement rate for top up only. The granular activated carbon are changed every 8 months, roughly. And that's driven primarily by the residual total organic carbon after the treatment.
Okay, thank you, Iván. María del Carmen Cano nos pregunta, te felicita también por la presentación y nos pregunta con los procesos de tratamiento que se proponen, ¿se eliminan de forma completa los contaminantes emergentes, tales como toxinas, hormonas, micro y macro y nanoplásticos?
Okay, so on this plant, most of the organic micropollutants are removed through the ozone and activated carbon filters process. The microplastics are removed through the ultrafiltration because the cutoff size is around 25 nanometers for these membranes. So effectively, you have no or very little microplastics, and certainly not more than what you would find from any drinking water plant taking surface water as a source water. The few things that are not removed, which I mentioned at the end of my presentation, are dissolved salts. So we see an increase of TDS at the moment. Another challenge is because there's ozonation process. So we are forming bromates in this plant, a little bit of bromates. The World Health Organization guideline is less than 10 micrograms per liter, I do believe. Sometimes at this plant outlet, we are a bit above that, but by blending with the other source water, it's okay. But the reverse osmosis membrane is going to help in dealing with that. So this plant has a multi-barrier process, but it's not tackling all the contaminants that you can find in the water. It needs a combination or an additional process step, but it comes with additional challenges as well.
Ok, gracias Iván. Ya para finalizar, María de Lourdes Correa nos pregunta si se usaron indicadores biológicos.
Like from bioassays. So we've done some work, and we continue to do some work, but it's part of a research project on the use of bioassays. At the moment, it's not something that is used on a regular basis for regulatory or reporting purposes. Even in Europe, for that matter, only in Switzerland, they are starting using bioassays on a regular basis. There's a very interesting project from the Global Water Research Coalition that is finishing, and the last presentation is in September in France, looking at bioassays and their significance for water use specifically. But for the moment, these are more a research topic than an actual water quality monitoring and reporting tool.
Thank you very much, Iván. Rafael, te devuelvo la palabra, ya prácticamente está todo contestado, con lo cual te dejo esos 5 minutos que necesitas. Tienes que activar el micro, por favor. Ahora sí, gracias, Rafael.
Ahora, bueno, decía que muchísimas gracias. Reiterar de nuevo nuestro agradecimiento a Iván y a los participantes por las preguntas y por sus respuestas. Obviamente es un proyecto que suscita múltiples preguntas porque estamos en el año 2022 y yo ahora haré algunas reflexiones que nos permiten comparar 1968, años posteriores del proyecto y año 2022. Algunos detalles que me parece interesante que pude observar durante la visita a esa planta donde nos regalaron esta magnífica botella. Aquí pone Windhoek. De hecho, la empresa explotadora tiene una fuente de agua que uno puede rellenar con esta botella, un poco protegida térmicamente, y beber el agua. Y yo recuerdo que fui uno de los que bebí el agua y me pareció pues un agua tan parecida a cualquier otra de las que había bebido. Como decía antes, Iván ha hecho referencia a las distancias. Namibia es un país que tiene 2,2 millones de kilómetros cuadrados. España tiene la mitad, medio millón. De manera que es 4 veces más grande que España. Y Windhoek está en el centro. Prácticamente es como un rectángulo y en el centro. Hay 700 kilómetros al río más próximo en el norte, en Angola, y hay 400 kilómetros, además de 1000 metros de desnivel, para llegar hasta el Atlántico. De manera que ahí las exigencias de transporte del agua son importantes. Ha hecho referencia Iván a ese closing the loop entre el abastecimiento, el saneamiento y el abastecimiento. Y durante la visita a la depuradora en Windhoek pudimos ver cómo es ese closing the loop a través de un humedal relativamente grande, donde el efluente secundario de muy buena calidad discurre, es expuesto al sol, a la temperatura, a toda la biota y a todas las plantas que crecen por allí, y de ahí es de donde se capta para ser sometido luego al proceso de regeneración. Hay un detalle interesante en lo que yo creo que los namibios fueron pioneros, es en esa distribución uniforme del agua regenerada, que se pone, de hecho se pone en los distintos depósitos de la ciudad, ¿no? Si yo recuerdo bien cuando me lo explicaron, no es tanto en la salida de la planta de potabilización como por una red que va a los distintos depósitos. Y uno de los énfasis que nos hicieron cuando nos explicaron esto es la absoluta necesidad de que esa distribución sea uniforme. Porque la falta de uniformidad, si hay un barrio que recibe más agua, fue lo que consiguió, lo que llevó a una ciudad en la otra parte del mundo, que es San Diego, a un fracaso rotundo cuando se vieron acusados de que se iba a regenerar agua, que se iba a poner en unos embalses que estaban abasteciendo a zonas menos privilegiadas, que resultó ser una fake news, pero esa noticia se convirtió en un reto casi insalvable a final de los años 90 y principio de este siglo. De manera que eso desde el principio los namibios lo tuvieron muy claro, había que distribuir ese 25 o ese 40% de agua regenerada por igual entre toda la población. Decirles también que en la página web de ASERSA hay varias entradas, entre ellas la conferencia que nos dio Piet Di Pisani, que fue el alma mater de todo este proyecto hasta el año 2015 o 2016, en que se jubiló, y confío que lo puedan acceder. Yo me voy a asegurar que todas las informaciones están ahí. De hecho, algunas de esas que nos ha mostrado Iván están ahí recogidas en tamaño un poquito más grande para que ustedes lo puedan ver. Porque, como les digo, en Windhoek celebramos me parece que fue el 12º simposio, el simposio del año 2013. Decirles, después de escuchar la presentación de Iván, cuando él habla de la necesidad, yo me he acordado del énfasis que les he hecho en múltiples ocasiones de que todas estas cosas, en particular la reutilización potable, directa o indirecta, se hace por pura necesidad. No es un hobby. Pero es que la necesidad en Namibia, como ustedes han podido ver, es una necesidad con todas las letras mayúsculas, no solamente la primera mayúscula. La N, la E, la C, la E, la S, todas las letras son mayúsculas, porque el agua es un recurso súper limitado. Y yo entiendo que en aquella situación, viniendo de momentos difíciles, recuerden que Namibia consiguió su independencia de África del Sur a final del siglo pasado, que Namibia está considerada un lugar de genocidio por otras culturas. El agua posiblemente no era la preocupación fundamental. No obstante, los investigadores sudafricanos, que fueron los promotores de todo este proceso, siempre defendieron la idea de que el agua debía de ser juzgada por su calidad y no por su historia. Y obviamente hay estudios, posiblemente no en la extensión y en el detalle en que hoy día los haríamos, o se están haciendo en Orange County, o se van a hacer en San Francisco, como nuestra colega Manisa nos va a explicar poco después. De manera que yo creo que Ivana ha mostrado lo que la ingenuidad humana y la necesidad humana puede hacer cuando es necesario. Los medios técnicos están disponibles. Se le puede añadir, como bien ha comentado, la desmineralización con ósmosis inversa para quitarle las sales. Ya nos lo anticiparon cuando estuvimos en el año 2013, que el hecho de reciclar el agua hace que las sales aumenten. El contenido de sales aumenta y, por lo tanto, en algún momento hay que plantearse la ósmosis inversa, que sirve para eso, para separar las sales del resto del agua. De manera que todo eso se está haciendo y es un proyecto de gran futuro de inspiración. En nuestras latitudes posiblemente lo tendremos que hacer de otra manera, con otros medios de comunicación. Piensen en la televisión en el año 1968, no sé cuántas televisiones había en ese momento en Windhoek, pero sin duda también tenemos los medios de comunicación, las estrategias de comunicación, los drivers, todo lo que nos hace falta para poder hacer todo esto. Y por tanto yo lo considero como un hito histórico digno de ser considerado y digno de ser emulado. Por decirlo de alguna manera, lo podemos mejorar. Siempre, todo se puede mejorar. De hecho, hay una expresión que muchos de ustedes conocerán en el mundo de la agricultura, que es: cualquier explotación agrícola es manifiestamente mejorable hasta que se llega a la ruina del agricultor. Es decir, uno puede mejorar todo hasta que llega a la ruina. Y es por eso que, como bien nos decía Iván, en estos momentos se están planteando desde traer agua del Atlántico, traer agua de Angola a 700 kilómetros, pero posiblemente la solución más factible sea volver a ampliar la reutilización potable directa, hacer la desalinización in situ de alto rendimiento para reducir las salmueras al mínimo. No sé si Manisha quisiera hacer alguna... Would you like, Manisha, to make any comment or ask any question to Ivan? Please, you have the floor.
Thank you. Well, I will just say that we are very inspired in San Francisco by the experience of Windhoek. I think it's incredible what has been accomplished. And, you know, I mean, I think we are all somewhere on this journey of water and water reuse eventually, maybe in different places because of the timing of our needs, but we are all on this journey. So I think we can all learn some lessons from each other. And certainly Windhoek is a huge inspiration for us in San Francisco, because we are looking at direct potable reuse. This is where we are going. And it's not, it's here now. We just completed a study to look at this. For me, I guess in California, and this is maybe a bigger question, but in California, we are seeing the regulations are moving towards reverse osmosis as the technology or the main component of the treatment, probably from a place of conservatism, wanting to go there. So it's very refreshing and interesting to hear Windhoek's experience and also the treatment process and how well a different treatment process has worked in the case of Windhoek. So it's something I think to pay attention to as the regulations evolve. I think in California, we might be seeing more conservative regulations coming first and then loosening over time, with experience, even from the necessary experience for the operators. We see a very high level of conservatism as the starting point in California. But I think necessity is the mother of invention, and as we have our needs evolve, we will see movement in the same direction over time. So I really appreciate your comments and your presentation.
Thank you. Well, en ese caso, solo me queda que agradecer de nuevo a Iván. Muchas gracias por la presentación y confiamos contar con tu colaboración en futuros proyectos de reutilización. Del tipo que sean, te invitaremos para que continúes aportando reflexión de otros lugares.
Con mucho gusto, Rafael.
Bien, pasamos por tanto ya a la segunda de nuestras presentaciones, a cargo de la señora Manisha Kothari, colega y amiga de fechas más recientes que el caso de Iván. De hecho, tuve el gran placer de conocerla y compartir con ella sus inquietudes durante su visita del mes de abril, una visita a las instalaciones de regeneración y de reutilización que tenemos en España. De manera que, de alguna forma, significa un halago para nosotros que alguien desde San Francisco quiera ver cómo lo estamos haciendo. Porque realmente tenemos un gran número de realizaciones que son dignas de valoración. Manisha es el gerente del programa de fuentes alternativas de suministro de agua. Esa comisión, ese grupo, ese programa, forma parte de la Comisión de Servicios Públicos de la ciudad de San Francisco, en California, que posiblemente, casi seguro, todos ustedes conocen porque es como la capital artística de California. De manera que, dicho esto, Manisha, tienes la palabra, 40 minutos, tu presentación está ahí y posteriormente tendremos un debate. Thank you. I guess you got the message.
Yes. Thank you so much, Rafael. It's such a pleasure to be here. And shall I share my presentation on my side, or will you have it there?
Please.
Okay, great.
Here we go.
Great. So yes, as Rafael mentioned, I am the manager of the Alternative Water Supply Program in San Francisco. This is a new program in San Francisco. So I'm with the San Francisco Public Utilities Commission, and we are a public agency of Northern California. A lot of similarities to Spain, and certainly we are moving, as I said, in the direction of Windhoek. So I am very pleased to be here to share where we are in our journey in San Francisco, and how we might draw some similarities, some lessons learned, and how we can work together as we move forward globally in this area. But I will share our experience here in San Francisco. Okay, so today I'm going to talk a little bit about our current water resources, because I think it's important to understand what our supplies are now and what they have been in the last 100 years, and then provide that context for where we are moving ahead for the future. And then finally, I would like to draw out some common themes and shared experiences, certainly from what we have heard with the history of Windhoek, but also from what I have observed when I was traveling in Spain in mid-April in France and Spain. I saw, again, some of these same themes coming out, and I would like to spend a few minutes to talk about them. So first, I'll just talk about our current water resources management in San Francisco, an overview of our water supply sources. Okay, so the San Francisco Public Utilities Commission, we are a public agency and actually a department of the county and city of San Francisco. So I think that's an important aspect. You know, in the 1800s, San Francisco's water was actually private first. But after the 1906 earthquake, which was a major earthquake in San Francisco, much of the city was destroyed by fires that came as a result of the earthquake. And it was at that time that the city decided that we will need to make this a public asset. Water should be a public asset. And at that time, that is when the city of San Francisco started to acquire water resources, and primarily, actually completely surface water supplies. One of the main things that was done in the early 1900s was we claimed water rights from about 300 kilometers away in Yosemite National Park. And this is the Hetch Hetchy Valley. So Hetch Hetchy and the Tuolumne River formed the first of our major water supplies. And we have subsequently also acquired other water supplies from watersheds, rainfall and runoff.
José Miguel, yo, permite que interrumpa, creo que deberíamos pasar a la segunda de las diapositivas.
¿Sí?
Esta, sí.
Yes.
Okay.
Okay, yes. So anyway, I just wanted to say that our water resources come from 300 kilometers away. Because this system that produces about 85% of our water from Yosemite National Park comes by gravity. We also produce hydropower generated by this water system. And so we also provide power services. In addition to water services to 2.7 million people, we also provide hydropower that is enough to serve the city and county of San Francisco, and all of the public resources, including San Francisco Airport, is fueled by hydropower, which comes from this water system. In addition to, so as I mentioned, this provides about 1 billion liters per day is the capacity of this system based on the demand. And within the city of San Francisco, we also provide wastewater services. So we provide water to a much bigger region, but within San Francisco, we provide wastewater, power, and water, all three. And in this larger region, we provide only water as a wholesaler. So we are both providing wholesale services as well as direct services to our customers. But you can see it's a very, very big system, again, powered by gravity, which is a very important distinction because in in California and around the world, pumping water and moving water is one of the biggest energy costs. So here we have energy neutral, or actually energy positive system, which is very hard to find something more cost effective and more energy efficient and more environmentally friendly than this kind of a system as far as movement of water goes. So this is an important distinction. The other important note is that 85% of our water, as I mentioned, comes from Yosemite National Park and the Tuolumne River, which is snowmelt. So much like Madrid, we are kind of relying on a very high quality snowmelt, which has been described historically as pristine, clean water. So safe, it tastes very good. So it is something that's very difficult to compete with as we look to the future, but something I wanted to note here as we move forward. Okay, so managing our water resources. The first, we are just talking about now our existing surface water supplies. The first things we have to do, conservation first. And this is definitely a policy of the San Francisco Public Utilities Commission, always conservation first. We do what we can with what we have before we look for new supplies. Then looking at non-potable, right? So once you have conserved as much as you can, you want to look at non-potable applications for water and how can you replace drinking water supplies with non-potable supplies. So recycled water, here I'm talking about centralized recycled water. Then you have on-site water reuse. San Francisco has been a pioneer in this area on reusing water on site at the point of use. So this is something that I will talk about a little bit more as we go forward. And then, of course, as Ivan mentioned, the low-hanging fruit, minimizing losses. What can you do to reduce losses in the system? We have a very large system, so there is potential for a lot of loss, but what do you do to minimize that? And then innovations. How do you leverage technology and partnerships to find new innovations? And this is all for managing our existing water resources. Okay, so conservation. In San Francisco, the consumption is about 150 to 170 liters per day. So by US standards, that's very good. I know by global standards, we could do better, and we are always looking to do better. We are also participating in the conversations about 50-liter challenge globally. There are many things that we should be moving towards, but by US standards, I will say that this is about half the average in California and around the country. So we are doing a lot of conservation, and that includes replacing fixtures. We have home audits, commercial audits. We give away free devices like aerators. We have rain barrels that we give as well. We have a laundry to landscape program. So those in homes, certainly who would like to connect their laundry for their home irrigation, we provide training on that. And then we provide financial incentives. We give rebates for devices like hot water recirculation pumps. We also offer grants. So we try to incentivize as much as we can conservation at a very local level. Then, in addition to that, recycled water. Okay, so centralized recycled water, and this is primarily for park and golf course irrigation, as well as cooling towers. And centralized recycled water in San Francisco, much like many cities in Europe, is a very dense urban population. And so there is, we do not have a lot of large, within the city, we do not have a lot of large backyards or gardens. We have public parks, and those we are irrigated or are moving towards irrigation with recycled water or purple pipe. But within the city of San Francisco, not a lot of large individual or private gardens and landscaped areas. So the opportunity for recycled water on a large scale is quite minimal. Once you get the golf courses and the parks, there's not that much more you can do other than retrofitting individual homes, which is extremely expensive and very difficult to provide recycled water on a large scale. So this is what has inspired us to move towards on-site water reuse. We have a lot of dense population, as I said, on the east side of the city. We have large new developments. So that is an opportunity for us to basically require new buildings that are coming to incorporate reuse as a strategy to minimize new demands on the system. So on-site water reuse, we have now rules, ordinances locally that we have passed that require buildings of a certain size and larger to incorporate systems to provide their own water supply for irrigation and for toilet flushing within the buildings. And we also provide technical assistance for developers who are thinking about this. We also provide a calculator that helps them estimate how much water they can save. And then finally, financial incentives. We provide grants to support not those who are required to reuse water, but those who would like to volunteer to reduce their water consumption on a voluntary basis. We also offer grants up to $1 million. So quite significant. In addition to that, on demand management, we work to minimize losses. We have losses under 10% in San Francisco, and we are moving towards 6%. This is our goal, and that is with leak detection technologies that we are testing, as well as pipeline replacements. In San Francisco, we have fully automated meters to check our water, and in the broader region, we are expanding that as well. So definitely a big push to minimize losses down towards 6%. And then we are also looking at innovations. So new innovations, for example, atmospheric water generation, we have a lot of moisture in the air here, a lot of fog for those of you who have visited San Francisco. So we are trying to collect this and create enough water for small community gardens, for small spaces. But again, this is something that we can look to do to minimize additional demands on water in the city. We also have adopted this approach of one water SF. In the United States, you see all over in Los Angeles and other cities, this approach adopted of kind of a cyclical thinking of water. What is water? Our traditional approach is this diagram on the top, which is water coming in to the city and then leaving as wastewater, right? You have a very linear approach to thinking about water resources. So we are trying to, this is the concept of the circular water economy. We are thinking about our urban watershed, essentially, and how can you reuse the water that you get before you discharge it as waste. So this falls into the concept that we are talking about as we look ahead in water. So looking ahead, what are the main pressures? And you'll recognize some of these as common themes, I think, globally. Drought, certainly the Mediterranean climate that we share in San Francisco with Spain and France. We see that this droughts with climate change particularly are becoming a bigger and bigger problem in terms of more severe and more frequent droughts we expect in the future. So this is a really big driver for us. Certainly resilience, with droughts and arid climate come wildfires. So how do we prepare and how do we have sufficient water supply, not just to fight the fires, but to have a resilient water supply? We have aging infrastructure in San Francisco. We have just recently invested almost $5 billion in updating our entire system, our regional water system, which again, we have a 300 kilometer distance from our main water supplies. So quite a large infrastructure that we have had to recently update, but we are just completing that now. I mentioned in San Francisco, we have a lot of new development. So how do you minimize new demands on the system? Then the need for stormwater management. And then finally, but also very important, in-stream flow needs. So we see certainly a trend here, and I saw this when I was in Spain as well. There's more pressure and more demand on water for people in urban areas, but there is also greater water demand for habitat and for the fish in the rivers. So how do you balance those needs? And how do you, as regulations move in that direction of needing to balance more and more those needs, how do you balance those needs? So these I would say for San Francisco, these are our two biggest drivers: our in-stream flow needs in the future and drought and future drought because of climate change. Those are the two, in our case, the biggest drivers. And so then in that context, we have a need to look at demands, look at supplies. On the demand side, as I have described, we are doing a lot of things. We're doing, I think, whatever we can, and we are always open to new ideas. We are not going to stop on trying to manage our demands. But at the same time, we see that there is a need for new supplies. And this is where alternative water supplies comes in, right? Once you have done as much as you can on using what you have available, you then eventually have to find new supplies. And we all know that water is finite, as a finite resource. So finding new supplies is a bit tricky. There is no such thing as new supplies. So how do you balance it? In San Francisco, we see that we have about a need of about 382 megaliters per day in future droughts, or we could be facing shortages of up to 50%, which, if you are already conserving a lot, is a very difficult thing to do. So this is what is driving our push and our search for new supplies. So what did we do in San Francisco? First, we looked at our geography and we said, okay, where are our facilities? Where is the infrastructure located? Where are our water treatment plants? Where are our wastewater treatment plants? Where are the pipelines that already exist? And how can we connect new dots to make new connections and move water more efficiently, and also leverage wastewater treatment plants as a resource? So if you take wastewater resource plants, the ocean, the bay, these are all now resources to us to identify new water supplies. So you can see these circles on this map. This is basically the areas where we created new projects by making these connections between wastewater and water, between the ocean and water, thinking about a broader urban reuse landscape. How do you identify new projects and new supplies? So these are our projects that we are looking at. And really, as I mentioned, there's a very limited opportunity for new potable supply, because now if you have done everything on conservation and you have done as much as you can on non-potable, you need to identify new potable supplies. And so for potable supplies, we have basically 4 options that we have identified. One is transfers. Transfers we find in certainly in Northern California, very limited opportunity for transfers, particularly as we look ahead into the future, because transfers means somebody else has excess water supply that they can provide. As there is more pressure on everybody, there is less excess supply available in other areas. So transfers we see it as a temporary or a short-term measure, but not a long-term sustainable supply source. So we do expect to rely on transfers, but for a small portion of our needs, and decreasing over time. Purified water. Now, purified water here is the term that we have adopted in California. It's used very commonly. It includes everything, all potable reuse from IPR to DPR. And we are really considering the whole spectrum of potable reuse. And we are referring to all of those aspects as purified water. So we are looking for purified water in San Francisco, like in Windhoek. We do not really have an indirect potable reuse option on the table right now. We are looking at direct potable reuse for San Francisco. But if you look at the broader region, there are other opportunities for indirect potable reuse as well. So we expect that the majority actually of new supplies would come from either indirect or direct potable reuse or purified water. This is why it's important to look at the wastewater treatment plants that are available in our area, not just those that we operate, but those that might be close to our service area, that we can enter into partnerships with others and leverage that as a new water supply for our customers. Desalination is another area that we are looking very heavily at, both regionally and in San Francisco. We are looking at this desalination. We have the ocean, we also have the bay, so we have the opportunities for seawater desalination as well as brackish water desalination. We have found, however, that desalination would be more expensive than purified water, because again, you get effluent from a wastewater treatment plant. It's much more stable and lower salt content, lower TDS level than seawater plant, for example. So from a cost and energy standpoint, we expect more of our supplies to come in the future from purified water than desalination. Then finally, storage. Because our need is really a drought need primarily, then we are able to think about leveraging storage, expanding storage, both above ground as well as below ground. So groundwater recharge, as well as surface water, dam raises and surface water supply increases. So storage is another way for us to manage for future droughts and our water supply. So those are really the areas we are concentrating on. There are many challenges. Certainly, I mentioned many of these projects are partnerships, so there might be very complex multi-party partnerships between water and wastewater, between agencies that have not traditionally worked together, but even between water agencies. We all have our different service areas. In the Bay Area, we have 8 major water providers. So we are working more and more together, but it's very complex, and we are learning how to do it. Also, certainly, as we look at potable reuse, it would require a lot of new operator training. This is a significant challenge for traditional water operators to learn how to work with wastewater and understand the characteristics of using membranes. Because our primary water supplies in the Bay Area are high quality surface water supplies, it requires very minimal treatment, if any. And so to now cross-train with wastewater treatment is definitely a new challenge for us. Of course, the high costs, high capital costs, and even bigger than the high capital costs are the high ongoing operations and maintenance costs. These are going to be very significant with these types of new projects, whether it's desalination or purified water. They come with a lot of high costs. There are also new regulations being developed in California. We expect new regulations for direct potable reuse by December of 2023. It is not yet regulated in California, but the regulations are coming, and the water utilities are participating in those in reviewing those draft regulations from the state. And then how do you integrate all of these things into your existing system? So you have a surface water system, and now you're introducing new systems, understanding the impact on the distribution network, and understanding, the distribution really is the key. How do you think about equity in terms of distribution? There is maybe not a real, but certainly a perceived difference in the water quality of these different kinds of supply. So how do you distribute in a way that is equitable and fair? And how do you distribute the costs as well, equitably and fairly? So these are some of the planning challenges that we are thinking about right now. With that, I want to really spend some time on some of these common themes. So first, maximizing efficient use of the existing supplies. I think this is something that we are seeing everywhere. Before you look to new supplies, have you done as much as you can with what you have? And so additional, reducing losses, this is a big one, but certainly if you can consume less, or you can grow in a way that is neutral or negative in terms of additional demand pressure on your system, this is the first step. The second step is really identifying all your non-potable demands, and how can you supply them with the appropriate water. The line we use in San Francisco is the right water for the right use. So are you matching the end use with the supply that you have available? Is it appropriate? Can you do more? So this is certainly something. We do not have a large agricultural area within San Francisco, but certainly in California is a very significant agricultural area. So using recycled water for agriculture is certainly one, but also we have Silicon Valley here. So for cooling towers and absolutely for irrigation and golf courses, these should not be using potable supply if you have an alternative. So this is the second step. Then the third step is testing new innovations and technological improvements. I mentioned, the atmospheric water generation. There are a lot of technologies, even within purified water or potable reuse, new monitoring technologies, new things that are coming out in this industry that I think is very important that we pay attention to, those that improve efficiency and also make it easier for us to operate, treat, and distribute water in the future. These are all important technologies to focus on as we move forward. How can we bring the cost down, and how can we improve efficiency? These are very important things to invest in. And certainly in San Francisco, we have an innovations program that is specifically to have some funding available to test these new ideas and innovations, and also working with universities in partnership to see what is being researched, what is on the forefront, and what can we move forward with in this area. Then after that, you have to kind of prepare from a budget standpoint. As a public agency, we have to prepare for the cost and the complexity of implementing new potable supply options, because all of them are very expensive. And it's an interesting paradox, if you will, that purified water or potable reuse is at the same time both the most luxurious water supply you could have, and also the most demonized, if you will. It's both ends of the spectrum at the same time, because it is a very expensive water to produce. And it's in fact a designer water, I would say, because you have a very good understanding of what's in the water and what's not in the water by the time you go through the treatment processes. At the same time, because of the source of that supply, there is a huge obstacle in public perception on acceptance of that as a water supply. So it's a very interesting paradox, and this is something that you really have to, I would say, these last two steps, preparing for the cost and complexity of new supplies, as well as engaging with public and leaders to get support for these new supplies, go hand in hand. And they really need to be sort of these long-term investments. One of the questions, I think one of the, that Yvonne was asked is, how long does it take? And you mentioned, Yvonne, 5 years to get this. In San Francisco, we think it will be 10 to 20 years. And really that is because the main thing is education and outreach. Engagement with the public is going to take a long time. You have to do demonstration projects. We have seen all successful projects around the world have a large-scale demonstration, as well as a sustained engagement with the public. So we are just at the beginning of that process now, and we expect that we will be doing that over the next 10 to 20 years, and then we will be ready to implement these projects. Certainly on potable reuse and desalination. We expect there to be some resistance, but it's a matter of engaging, answering questions, and being very, very transparent. That is, we are certainly committed to that for the long term if we want to be successful with these projects. So really, these are, I think, I'll go back to what I started with in the beginning. These steps, if you will, are things that are common wherever we are in the world, and we are thinking about water supplies. Where you are in this journey can differ, it can really vary, but some people are still able to manage all of their demands with step number 1, which is fantastic. But I think eventually we are all going towards reuse and maybe some form of a combination of desalination, transfers, reuse, and storage. But as we get there, it's important to keep these in mind and to learn from the experiences of those like Windhoek who have gone before us. So this is, those are my comments, but I'm happy to answer questions. Thank you.
Thank you, Manisha, for your excellent presentation. You have covered quite a few of the same concerns we all have when facing current situation. As a matter of fact, the idea that comes from your presentation and Ivan's presentation is we have to accept, we have to realize that we are in a different condition. We cannot permanently refer to what it was 10 years ago. And as a matter of fact, I came to the idea that we have become accustomed now to this idea that when you buy now to get a ticket for the airline, you know that if you buy the ticket now, if you find a ticket, it may have a cost. If you wait until the last minute, the cost may be much higher than that. So in those cases, there's not a question of saying, this is very expensive, this is more expensive. This is what it is. Do you need it now? You have to face the challenge. Okay, so we have time for questions. I will open the floor for the participants. Then I will offer the floor to Ivan in case he likes to make a comment or a question to Manisha, and then a roundup. I will wrap up the session. I will just make a few comments and questions. Please, José Miguel.
Sí, Rafael. Bueno, pues ya tenemos varias consultas. Una primera que te pido que se la traslades a Manisha.
Yes.
Nos pregunta Margarita Vera lo siguiente. ¿Podrías decirnos, Manisha, qué tipo de tecnología estáis utilizando para detectar fugas de agua y si habéis tenido éxito?
All right. Manisha,
Yes.
You understand what technologies are you using for detecting water leaks, and how was your success with that?
Yeah, I'm actually not an expert on water leaks, but this is an information I'm happy to get for you. We are testing a few different technologies right now in different parts of our system. We have not done a large-scale implementation, primarily because, as I mentioned, we have invested $5 billion in upgrading and retrofitting our entire system. So actually, we in the broader system, throughout the Bay Area, we don't have a lot of leaks right now. It's primarily in San Francisco that we are concentrating on different technologies for leak detection, where our pipes are quite old and in the process of being replaced. But we are certainly looking at several technologies, I know, and I'm happy to get back to you with more details on that if you're interested.
Okay.
Rafael, César Baños nos pregunta que cuánto cuesta reciclar 1 metro cúbico de aguas residuales, cuánto le cuesta a ello, y si le cuesta más que reciclar ese metro cúbico con tratamiento de osmosis inversa de agua de mar.
Okay, the question is, what is the current cost for you for water recycling, 1 cubic meter or 1 gallon or whatever?
Yeah.
In California, they use this acre foot, which is 1, 2, 3, 4 cubic meters, okay?
Is that what it is? Okay.
1, 2, 3, 4 cubic meters. How much is the cost for reclaiming water? How much is the cost for desalination, seawater desalination, ocean water desalination?
Yeah, okay. I just do a quick calculation. So I don't know. So, okay, so about for recycling, it really kind of varies from place to place because it depends on the distance from your treatment plant to your distribution network. We think about it as the cost per mile of pipeline, so we think about it as, because the biggest cost is often the pipeline cost, because we are in a very dense urban environment. So trying to tear up the streets to put a new purple pipe, this is a really big cost. So the cost is about $5,000 per acre foot on average. It could be even double of that. So that would be, you said 1,234 cubic meters per acre foot. So that's like 6.2 million per cubic foot. Is that right?
Just
cubic meter. Yeah.
My suggestion is just present your numbers in your units, and then we will make the calculation, because otherwise, Murphy
it really can vary as much as $5,000 to $10,000 per acre foot for recycled water, which is why, again, you really have to think about where it makes sense, where you have non-potable end uses and sufficient end uses to justify that. For desalination, by contrast, could be on the higher end of that, but not much more, because here, what the difference is, the treatment cost is high, but your distribution cost is not so high, right? So that's where you make up the difference. That's why it's not so different, the cost between recycling and desalination in our case, because the cost of the distribution system is so high. So it's really actually about the same.
Rafael,
Yes.
Rubén Vandrán nos pregunta que a cuánto debería subir el precio del metro cúbico para poder asumir las inversiones que ellos tienen en mente, y de cuánto es la inversión prevista aproximadamente y los plazos de implementación de estos sistemas.
Three questions, complex questions. First, how much should it cost the water in order to cover the expenses you are contemplating now? And how much is that expense that you are contemplating for the future, investment for bringing about all these water that you need in the future?
Yeah. So our cost right now, I mean, as I said, our costs are quite high because we have just done a major upgrade to our whole system, and our customers are paying for that now. So right now the cost is, about $3,500 per acre foot. The cost in the future is going to go up significantly with these new investments, not just as I mentioned earlier, not just capital, but ongoing O&M costs. So these are going to be permanent cost increases over time. We have not yet determined what the cost per acre foot is going to be of these projects. As a program, thinking about all these alternative water supplies, we expect it to be, again, on the order of billions of dollars. So, $5 to $10 billion of new investments to secure these new supplies. So, which is basically the equivalent of upgrading our entire system, at least doubling those costs as we invest in these projects. That's why, again, the first step is always to try to maximize the efficiency of what you can with what you have. And we want to make sure that we are doing that very clearly, very deliberately, and very openly before we look at new supplies. But we don't see a future where there are no new supplies, where we are not looking at potable reuse, where we are not looking at expanding storage, where we are not looking at recycling as much as we can. We don't see how that it would be possible to meet the needs of our customers in the future.
Sí, Rafael. Salvador Santos nos pregunta que cuáles son los principales criterios en cuanto a tecnología, calidad y manejo del agua para tener agua segura para el reuso potable indirecto. ¿Cuáles serían esos criterios?
All right, the question is, what would be the criteria for selecting the technology you will need in order to produce this purified drinking water quality?
Yeah. So a lot of the technology is going to be dictated by the regulations in California. We can see, based on the draft regulations that are coming out, that those are basically risk-based approach to thinking about regulations. And that means that they are looking at log reductions, the number of log reductions that you can achieve through different treatment processes. And there will be quite high for potable reuse, for direct potable reuse. Those requirements will be very high. So that will be very limiting for us from a technology standpoint on what can achieve, which kinds of treatment can achieve those very high log removal targets. We expect, you'll see a lot of the familiar things that Ivan talked about, ozone, bioactivated carbon, reverse osmosis, as I mentioned, is in the case of California, kind of central, but also MF or UF, like ultrafiltration, microfiltration, and then advanced oxidation. So really, any treatment you can think of will probably be part of the treatment train in order to achieve the log removal targets that we will be expected to achieve.
Sí, Rafael.
Yes.
Fernando Anaya nos hace una pregunta, lo que no sé si procede o no, que nos dice que cuál sería el costo de operación y mantenimiento de una planta de desalinización y con qué frecuencia se deberían cambiar las membranas de la osmosis inversa.
That's a very technical question. If I understand correctly, Jose Miguel, the question is, what is the cost of operation and maintenance of the desalination facility? And which would be the frequency for changing the membranes? ¿Esa es la pregunta, Jose Miguel?
Sí, sí.
Okay.
Yeah, so, in our case, we are only in planning. We do not actually operate any desalination plants yet. So Ivan actually might have a better answer to this question. We have estimates based on what we expect. The problem for us is, as I outlined, the demand for water for us, particularly in the future as we think about desalination or purified water, is that we only need the water in a drought. We don't need the water all the time. Our surface water supplies, we think, are sufficient to get us to 2045. But when we are in a drought, our supplies go down a lot. So, the replacement of membranes and the cost of the membranes is actually a very significant issue for us, because operating these plants intermittently has its own challenges, and these membranes are quite sensitive. So we expect that when we operate, if we do not operate at 100% or close to that all of the time, that the cost for us for changing membranes may be higher than the normal cost if you are operating all the time. So for us, I expect that the cost of operating will be a bit higher because of that intermittent need that we have. But Ivan, you might have some additional thoughts on cost.
I think your answer is quite right and quite accurate. I mean, there's nothing more expensive than a plant that is not running. That would be the answer. This is happening. I mean, there are some cases, if you refer to Australia, for instance, they've got 5, 6 large-scale desalination plants, and 4 of them are not running on a regular basis. So these assets are used as a drought response assets, but effectively the capital amortization and the OPEX for water that is not produced is huge. If you go to the Middle East, where the desalination plants are very large and used to their full capacity, you see that the cost of water is about 50 cents per cubic meter, which is just amazing. But that's also related to the cost of labor, the cost of raw material, of construction, and so on these countries. So the parallel cannot be done. For a plant that is running consistently and good quality water and pretreatment, the membrane replacement rate should be about 5 years on the reverse osmosis membrane. So about 20% per year, effectively.
Good.
Sí, Rafael, ya iríamos con la última para Manisha.
Okay.
Nos pregunta Max Castillo que si ellos en el proyecto han valorado los efectos de la salmuera en la vida marina con el proceso de osmosis inversa.
Okay.
Los efectos que produce la salmuera.
The question is whether you have considered the detrimental effects of salt concentrate from the demineralization processes.
Absolutely. This is a huge issue and huge concern for us. Brine management, I think Yvonne mentioned it as well. Brine management is a big issue, and maybe one of the things that reasons why reverse osmosis is not really considered in Windhoek, in the case of Windhoek. But in California, since this is the standard, brine is at the same time a big issue. So we are studying all over California. We are working with universities. This is a big topic for the universities. Stanford University is looking at this. Berkeley, there are some other universities as well looking into brine management. And what can you do to recover resources from the brine? So resource recovery, if there are minerals that you can reuse either on site or nearby, that is the preferred. What can you take out before you discharge? And then, what are the opportunities to dilute? Because you're not increasing the volume, you're increasing the concentration of anything you have taken out of the water when you put it back in. So dilution has been the sort of traditional way of thinking about. You go far enough out, you dilute enough, and you're okay. But we need new solutions, and this is where technology can be a huge help as well on resource recovery. How can you take things out, extract them, and put them to beneficial use to the extent possible?
Thank you, Manisa. That is. Rafael, te doy ya la palabra, ya está todo contestado y vamos cerrando poco a poco.
Bueno, muchas gracias, José Miguel. Muchas gracias, Manisa, por la presentación y por el debate y el ofrecimiento a facilitar esa información. Yo sugiero que las personas que tengan deseo de conocer algún detalle, o bien a través de José Miguel, te puedan pasar la petición, o bien consultar en la página web. Nos puedes facilitar la página web de esa Comisión de Servicios Públicos de San Francisco, donde ellos, los interesados o interesadas, puedan consultar ese tipo de información. ASERSA particularmente recoge un buen número de esas referencias. Para entrar en detalles más técnicos y resumen de la presentación, yo querría hacer una serie de aclaraciones técnicas y otras menos técnicas. La primera de todas, recuerden todos ustedes que el billón que Manisa utiliza no es el billón que utilizamos en Europa. Normalmente los norteamericanos utilizan el billón que se llama corto, que es el equivalente a nuestro millardo. El billón para nosotros en Europa normalmente es el millón de millones. De manera que atención con estos cálculos. Segundo punto muy importante, y es que en California el agua tiene coste. El agua no es un bien público de coste cero. El propietario del agua, el que tiene la concesión, San Francisco, que tiene ni siquiera concesión, es una propiedad. En un momento dado, en el 1900, principio de 1900, alguien se fue a la montaña de la sierra y dijo, este agua es mía. Y ya está. Y esos derechos del agua comportan un coste que hay que sumar al coste que significa el transporte. Y digo esto porque, como bien decía Manisha, el tema de la reutilización no potable puede ser muy interesante, pero en ese caso ya no es tanto el coste del agua, sino el coste de transportar el agua. En una ciudad tan extensa como San Francisco, llevar esa segunda red de distribución del agua puede significar un coste muy superior al coste propiamente del agua. Otra cuestión que quería comentarles es, les habrá sorprendido, y a mí me sorprende muy favorablemente porque lo conozco muy bien, esa posibilidad de recoger recursos hídricos a partir de la atmósfera. Pero eso es porque San Francisco tiene una climatología muy peculiar. Y es que todas las tardes viene el fog, sube por las colinas y baja hacia la bahía y lo inunda todo de humedad. De hecho, si alguno de ustedes tiene intención de viajar este verano y pasar unas semanas, unos días en San Francisco, cosa que yo les animo a que hagan, no se olviden de llevarse el chubasquero y sobre todo llevarse un parka, porque en la costa de San Francisco, cercano al Golden Gate, pueden pasar mucho frío. Todas las tardes, a partir de las 6 o así, tienen el fog. De manera que eso sí que es una fuente. En nuestro territorio yo creo que no tiene ningún interés, y menos en las zonas áridas en que nosotros estamos. Otro detalle ya más técnico, se ha hablado de la combinación de carbón, como han utilizado en Windhoek, y como también carbón activado, y como también se está impulsando como alternativa a la ósmosis inversa en la costa este de los Estados Unidos. Son numerosos proyectos en la costa este que utilizan el carbón como forma de absorbente de los compuestos orgánicos, contaminantes emergentes, en lugar de la desmineralización. Y es económicamente, según parece, viable, digno de considerar. Y es lo que han venido haciendo en Windhoek, pero como les decía, en Windhoek, después de tantos años de reciclar el agua, esa economía circular, las sales se acumulan y antes o después hay que llegar a la desmineralización. De manera que ese es un equilibrio. En muchos de nuestros casos utilizamos la ósmosis inversa como forma de quitar contaminantes orgánicos, pero se puede utilizar el carbón, pero llega un momento en que hay que utilizar el desmineralizador para quitar la sal. Y por último, quizá también comentar que la parte positiva de decirle a Manisha, bueno, dos cuestiones, quizá una más técnica para todos ustedes que han hablado de si la desalinización, el coste y demás. Yo les puedo anunciar, lo pueden ver en la página web de ASERSA, muy bien recogido, que en estos momentos la Comisión de Asuntos Costeros californiana ha prohibido la instalación de una planta de desalinización costera en Huntington Beach, que es una ciudad al sur del estado, no tanto por la problemática del vertido de las salmueras, sino por la problemática de la captación del agua con toda la flora, toda la vida acuática y los efectos que puede tener desde el punto de vista energético y sobre todo si se instala en un lugar que está llamado a ser inundado en el futuro. De manera que en este momento las perspectivas de instalar una desalinizadora en California son mínimas, tanto si es en el norte como en el sur, más allá del coste. Y ya por último, decir, si yo he entendido bien, decía Manisha que con unos 38.000 metros cúbicos al día, si he entendido bien, San Francisco tendría resuelto su problema, que son unos 10 millones de galones al día, ¿no? 10 millones de galones al día son eso, unos 40.000 metros cúbicos al día. La verdad es que es un volumen relativamente pequeño, sobre todo pensando que en el sur, en Orange County, tienen una planta que hace 10 veces eso todos los días. 380.000 metros cúbicos, pero la parte positiva, digamos, la ventaja que tienen los californianos del sur es que pueden almacenar ese agua. Tienen acuíferos que están sobreexplotados y que resuelven esos temas que nos planteaba también Iván Pusat y Manisha, de decir, la planta más cara es la que no funciona todo el tiempo. si uno tiene una planta que puede producir todo el tiempo y si no se utiliza el agua, se puede guardar en un acuífero, en una balsa o en un embalse, esa es la solución óptima. Además de que eso hace que la reutilización se convierta en reutilización indirecta. Y la normativa para esa está ya aprobada y ya está funcionando. De manera que, como se dan cuenta, la complejidad de todo este proceso no solo es técnica, económica y, por supuesto, cultural y educativa. Yo tengo mucha ilusión de ver cómo lo van a resolver en San Francisco, porque antes o después nos afectará y nos ayudará también a nosotros a contemplar las soluciones. Manisha, no sé, I don't know whether you have any other question. I don't know whether you got my message, although I did speak slowly. Ivan, do you have any further question or any further comment before we close the session?
No, no further question or comment. I think it was very interesting to hear what Manisha had to say in terms of planning. You know, it's a few years back from a few years ahead in terms of planning compared to the solutions that are being implemented or have been implemented. But it's very good to see the path forward. So very interesting, and I look forward to see the development in the coming years and decades.
Thank you. Manisha?
Yes, no, I appreciate very much the opportunity to speak today and also to listen to the questions and, of course, to Yvonne's presentation and learn more about Windhoek. No, I appreciate it very much, so thank you.
Please keep us up to date on what you do, because we are really looking forward to do something. And I guess, again, the key word will be necessity. If the drought intensifies or continues, we are going to speed up. No question about that.
That's right.
Thank you. Gracias, José Miguel. Gracias a todos los que han seguido la presentación. Dentro de muy pocas horas estará disponible en el servidor de aguasresiduales.info, y en cuestión de unos días el vídeo y las presentaciones estarán también disponibles en la página web de ASERSA. Les reitero que pueden mirar y explorar, porque en ASERSA recogemos muchas noticias relativas a la situación californiana, sobre todo del sur, que son los que tienen unas necesidades más inmediatas. E igualmente tenemos referencias interesantes de los años 2013 y posteriores de Windhoek. Y nada más, que pasen todos muy buen verano. Y nos vemos a la vuelta al principio del otoño. En octubre organizaremos de nuevo webinarios que espero sean de interés para todos ustedes.
Thank you, Manisha. Thank you, Iván. Gracias, Rafael. Y nos vemos a la vuelta del verano. Gracias a todos.
Que vaya todo bien y que no tengamos demasiadas sequías.
Buenas tardes para todos.